I stopped sending every AI task to the same model. That sounds obvious, but it is how a lot of local AI setups begin. You install one model, point every script at it, and eventually one slow job blocks something that should have taken seconds. My setup now gives applications one OpenAI-compatible entry point on localhost, port 11435. Since July 12th, that stable local address is forwarded to the authoritative router process running loopback only on the older laptop at port 18135. Integrated applications still call the same address, describe the work they need, and let the router resolve a configured model and service. In this video, I will show one real routing path, make one synthetic request, and inspect the route that actually served it. The primary machine has an RTX 5090 laptop GPU with 24 gigabytes of VRAM. It runs a pinned Ollama instance for the normal interactive model and a second local Ollama instance for batch models. The older laptop has an RTX 3070 laptop GPU with 8 gigabytes of VRM. It now hosts the authoritative router process as well as the separate fallback Ollama service. The important idea is not the number of machines. It is the boundary. Each integrated application can talk to the router instead of knowing where every configure model lives. First, I query the health endpoint through the caller-facing address on 11435. The current response reports authoritative router port 18,135 and shows 3 upstream services up, local and local batch on the RTX 5090 machine, plus old laptop on the RTX 3070 machine. That difference between the queried and reported ports is expected after the cutover. I am deliberately hiding cloud provider readiness, credentials, network addresses, and request history. None of that is needed to explain the architecture. The model endpoint shows what the primary local Ollama instance currently exposes. It is not an aggregate inventory for every service. An inventory is not the same thing as a routing decision. A model can be installed without being the right default for a task. Here's why I do not use the biggest install model for everything. The main interactive route is currently configured around Qwen 3.6:27b for native Ollama API requests to the 2 services on the primary machine. The router is configured to inject the GPU setting so oversized work fails into its configured fallback path instead of silently spilling onto this machine system RAM. The OpenAI-compatible request I am about to show does not exercise or prove that native API enforcement, so I treat it as a separate policy, not a result of this demo. That is an operational choice. I would rather see an explicit failure or fallback than discover that an automation job has been crawling through RAM without an obvious signal. The router can identify intent in 3 useful ways. First, an application can use a virtual task name in the model field, such as general, writing, coding, or structured. Second, an application can identify itself with the xcaller header or a caller-specific URL prefix. That lets one central configuration define the default task for each real application. Third, supported real model tags can be requested directly, but task names and aliases are resolved first, and the batch service is targeted separately. I am using a virtual task in this demo, so I do not need to rely on model tag pass-through. There is also an optional node choice. New targets the RTX 5090 machine. Old targets the RTX 3070 laptop. For a non-streaming task route that has both local candidates, both races those candidates. With no explicit node, the selected task route follows its full configured candidate chain. For the demo, I am using synthetic purchase order text. There is no customer data, API key, or private prompt on screen. The request goes to the standard chat completions endpoint. Its model field is structured, and the response format asks for a small JSON object with supplier, currency, and total. The local portion of the current structured rule selects Qwen 3.6:27b on the primary service, followed by Qwen 3:8b on the old laptop. The live rule also has deeper cloud candidates, which the sanitized fixture omits without pretending they do not exist. Now I send a request. The response body should satisfy the schema, but the body is only half of what I want to inspect. The router also returns route metadata in response headers. the resolved task, actual model, node, and routing mode. The first rehearsal exposed an important distinction. The model returned valid JSON with the correct keys and number, but it copied the buyer into the supplier field. The schema was valid. The meaning was wrong. I changed the synthetic input to explicit uppercase labels, set deterministic request options, and made the capture helper compare the response with a separate expected value file. A schema is not a semantic guarantee, so the demo now fails visibly if those values do not match. After the July 12th router placement cutover, I ran the hardened fixture twice through the caller-facing 11,435 endpoint. Both responses matched the expected values exactly. The first run took 54.806 seconds end-to-end. NVIDIA showed 3,726 MB of whole GPU memory used before the request and 21,798 MB after it. The second run took 42.401 seconds end-to-end. NVIDIA showed 21,794 MB immediately before and after. Both runs resolved task structured. Actual model Quinn 3.6:27b, node new, and routing mode failover. Failover names the sequential strategy here. Node new confirms that the primary model service handled both requests. Before rendering this private draft on July 13th, I ran the same sanitized helper again. The semantic check passed. The request took 41.116 seconds end-to-end, and the whole GPU snapshot moved from 22,182 to 22,186 MB. It again resolved task structured. Model Quinn 3.6:27b, node new, and routing mode failover. That fresh run is consistent with the second rehearsal, but 3 observations are still not a benchmark. The wall times can include queuing, loading, forwarding, HTTP overhead, and generation. The memory values are system-wide snapshots, not per request or per model allocation. Those are recorded observations, not benchmark claims. One request is a demonstration, not a statistically useful performance test. If I later publish a speed comparison, I will use repeated runs, record warm versus cold state, and publish the method. The fallback behavior is intentionally explicit. An automatic request can move through the task's configured candidates when an earlier one fails. Pinning new or old means that service only. For a compatible non-streaming route, choosing both starts the 2 local candidates and prefers the new machine's successful result. Streaming requests do not use that same behavior, so this demonstration is non-streaming. In a rehearsal, the mode header said failover, which names the sequential strategy. The node header said new, proving that this request stayed on the primary service and did not actually fall back. Some task routes, including the structured route, can contain cloud legs after their local candidates. That is a policy decision in the routing file, not an accidental SDK call hidden inside each application. For data that must remain strictly local, I need to pin an appropriate local service or use a route whose complete candidate chain is local. For other work, I can choose a different cost, latency, or availability trade-off while the application keeps the same endpoint. Centralizing this logic has costs. The router becomes infrastructure that needs health checks and tests. A bad rule can affect several applications. Changing a model can change output quality even when application code stays untouched. And because this setup stores full prompt and output history in a local SQLite database, the history must be treated as sensitive. For this video, I'm showing only handwritten fixtures and cropped, sanitized output. I will not show router keys, OAuth files, raw history, personal prompts, provider readiness, or private network details. The benefit is that model selection, fallback behavior, and GPU policy live in one place. The routing file hot reloads for rule changes, so I can tune a task without editing every caller. The repository also has an offline routing test that I run before treating a change as safe. So the pattern is: one stable endpoint for applications, virtual task names for intent, explicit caller and node overrides when they are actually needed, an explicit GPU policy for native local API routes. configured fallbacks instead of invisible slowdowns, and response headers that tell me what really happened. Next, I will turn this into a repeatable measurement. Multiple task types, warm and cold runs, route metadata, end-to-end wall time, and clearly labeled whole GPU memory snapshots, all captured without leaking prompt history or credentials. If you are building local AI automation, start by separating the application from the model address. Even with one GPU, that boundary makes the system easier to change, test, and understand.